All right. So, what was the main point from the knowledge chart? Let's start there. That's going to give us into where we're going next.
Simple machines.
Simple machines. And what do simple machines do?
They change
Simplify our lives.
the magnitude and direction of the force.
They change the magnitude or direction of a force. Okay? To make things simpler in our lives. Now, so the difference then, well, give me an example of a simple machine. One of the simple machines. Okay, a pulley, a ramp or an inclined plane, lever, wheel and axle, wedge. And then there's a special type of inclined plane. If you take an inclined plane, you wrap it around a post.
Spiral.
Sure. Okay. So those are the simple machines. Let's talk for a minute about the inclined plane. Let's say I want to move this ball, and I want to get it up into the back of a moving truck. Okay? Now, I have two options for getting this ball in the back of the truck. Or I have more than two options, but what are two options that I have?
Kick it up.
Pull it, pick it up, and place it into the back of the truck. Right? Now, what does that require? How much force does that require to pick it up, put it directly in the back?
You have to work against gravity.
Yeah, this is a 16 pound. So 16 pounds of force, right? Yeah. So yeah, it's 8 kilograms-ish, 80 newtons of force, right? Okay. But what if I put up a ramp and I roll the ball up the ramp? Do I still have to apply 80 newtons of force? Think about the force diagram. If I'm lifting, energy is down, and my force up has to equal mg. But if I'm pushing it up an incline, then yeah, the normal force is helping take care of a good chunk of mg, and I only have to push against the sine of the angle component of mg. Right? So by pushing it up the incline, I get to use what?
Less force.
Less force. Same thing with a lever. If I give me an example in everyday life of a lever.
Oh, hammer.
Okay, a hammer is a type of lever where I apply an action force down here near the fulcrum, causing there to be a work force to the other end. Now, for a baseball bat, okay, let me ask you this. Am I using more force down here or less force down here than what's happening up here?
Less forces.
Really?
And because you have to use more forces to put further down. Because you have more stuff to move.
That's why you do something in grade 2.
That's why a mouse got caught.
Exactly. Yeah. Let's think about the baseball bat. When you're in Pee Wee, what do they tell you to do?
Choke up.
Choke up. Choke up. Why did they tell you to choke up?
It's not safe.
because, and we'll talk about the reasons why later when we get into rotational motion.
It's not as hard to start, this one.
Exactly. Because it takes less force from here than it does from here. Okay? So that's one example of the type of lever. But we're more used to the type of lever as Mason just said, the light switch or the door handle, where I reach out on the outside and push down. If I want to open that door over there, I don't reach in here and push down. That takes a lot of force. Instead, I reach out here on the edge and push down. Because that's what the purpose of the simple machine is to allow me to use less force. Actually, that's not true. Oftentimes, the purpose of the simple machine is to allow us to use less force. Sometimes, like the baseball bat, we go ahead and use more force because of what it does at the other end. And that's the point that we're about to make right now. Do I get that to use less force for nothing? What's the trade-off? What do I have to do? Look at the difference between this and this. I have to move it farther. Right? Here, I use less force, but over a greater distance. Here, I don't have to move as far, but I have to use a greater force. This relationship between force and distance is what we call work. Work is force times displacement times cosine theta. Now we'll come back to the cosine theta in just a second. Let's hammer out the force and distance thing for a second.
Who said that?
Whoa, who said Alex?
All right, keep this up. So, now, when I first start this ball moving, I'm going to push it with my foot that way. Right now, as I'm exerting a force on the ball, did I do work on the ball?
Yes.
Okay, positive or negative work?
Positive.
Positive, because which way did I push it? Forward. And which way did it go?
Forward.
Forward. So I did positive work to move it forward. Now, here. Now it's moving towards the front of the room, and I put my foot and I stop it like that. What direction did I apply the force? Well, point. That way, right? I pushed that way on the ball. Which way was the ball moving?
That way.
That way. What's the angle between those?
180.
180. So I did
Negative. Wait, if you
negative
that
work.
way, and it was working that way, or it was moving that way, how does that work?
Just like this. Here it comes.
So you have to go force to stop it.
See?
Oh, okay. I thought you meant when you pushed it that way.
Yeah, not the original.
Okay.
Two. Right?
And what if you roll the ball into the wall?
We're getting there.
Okay.
Okay. So, positive work when I'm pushing in the same direction as the displacement. Negative work when I'm pushing against it. Now, watch this. Right now, what kind of work am I doing on the ball?
Negative.
Right. Once it's moving, I'm only pushing up.
Negative.
So what direction am I pushing? What's the direction of the force? Up. What's the direction of the displacement?
Forward.
Forward. What's the angle between those two?
90.
90 degrees. What's cosine of 90? Zero. So when I'm pushing perpendicular to the motion, I'm not doing any work at all.
Seems like you're doing more work.
Yeah, it seems like I'm doing more work. But really all I'm doing, seems like what I'm doing is doing more work because I'm having to hold up the ball, right? I'm having to exert a force. But I'm not doing any work on the ball because all my force is just canceling out regardless. Yes, Connor? Yes.
So what happens when you're carrying a really heavy box?
No work, no work.
That's no work.
Right.
It feels like work.
It feels like a lot of work, right? Because again, I'm having to exert a force, and how am I exerting that force? Well, my muscles are contracting, and that's using energy. And so I get tired from exerting that force. But I'm not doing any work on the ball.
So you can use energy while not working.
You can use, yes,
Without working on another object.
you can use energy, but not be doing work on an object. Okay? And we're going to talk about how you see this in calculus.
That doesn't make any sense. That's definitely what he's
No, you're just not
Bear
putting
with
any work on the object.
Right, I'm not doing any work on the object.
You're doing
Now-
work on yourself. You're working yourself.
Now, let's talk about quantifying this a little bit. If I take this ball and we said it has a mass of what? 8 kilograms, and so the gravitational force on it is 80 newtons. So how hard do I have to pull up to do this, to lift it up with constant force?
More than
Or constant velocity?
more than
To lift it up with constant velocity?
80.
Exactly 80. Remember, constant velocity is the same thing as no velocity. Because there's no acceleration, therefore there's no net force. Why?
And first law.
Newton's first law. I told you you didn't believe it.
I believe it.
I keep telling you, you don't believe Newton's first law, even though you think you do. Once I get this thing in motion, it wants to keep going up. All I have to do is keep gravity from stopping it. So it takes a little bit more than 80 to get it moving, but then once it's moving, I go 80, and then it takes a little less than 80 to stop it. But for the most part, as I push up, I'm pushing up with 80 newtons of force. All right? So, let's quantify this. If, in this example, my force is 80 newtons, so the units are newtons, and let's say I raise it up 1 meter. What was cosine of theta? 1, because the force was up and the displacement was up, and so they're in the same direction, so the angle is 0, therefore cosine of 0 is 1. So that becomes 1. What units do I end up for work? Newtons times meters, right? Newton meters. But once again, we get tired of saying Newton meters, and so we say, hey, we got any dead guys laying around who did some physics stuff. And we say, ooh, there's one. There's this French physicist named Joule. All right?
That's the same thing as energy, right?
So the unit for work is joules. The abbreviation is capital J. Now, what are the units for cosine theta?
Please. Just kidding. No units.
Good, no units, because it's what? It's a ratio of 2 sides. It's a length divided by length, so that's dimensionless, so that has no units. So work, the unit for work is joules, capital J. So, how much work did I do lifting this 8 kilogram ball 1 meter? 80 joules. And then as I lower it back down to the ground, how much work do I do?
Negative 80.
Negative 80 joules. Good, because I'm doing negative work because the force is up and the displacement is down.
Is this a capital J or a lowercase j?
Capital J. Joules. All